The word moss city, the vertical forest living on old buildings. At first glance, under our warm seems lifeless. Brick, concrete, plaster, stone, hard surfaces built to defy space, hold weight, and resist weather. But time changes words in ways most people never noticed. Rain touches them, dust settles into tiny pores, shade lingers in the corners where sunlight rarely reaches. Moisture rises slowly from the ground. In the overlooked conditions, the world begins to grow a second skin. That skin is moist. What appears to be a soft green stain spreading across old buildings is actually the beginning of a vertical forest ecosystem. Mars is often the first visible colonizer of worlds, transforming plank architecture into a living habitat. It needs almost no soil, no deep roots, and very little space. A few rough pours and stone, a same in old mortar, or a permanently shaded edge is enough for life to begin. The process starts with surface memory. All words are never truly smooth. Over the years, microscopic pests from as rain hit, pollution and temperature changes erode the material. Dust settles into the pits. Airborne spores lodge in their texture, tiny fragments of leaves, pollen, soot, and organic particles stick to damp surfaces after mist or rain. The invisible deposits create the world's first biological layer. When most spores arrive, they only need one thing: repeated moisture. Unlike larger plants, moss do not depend on roots that dig deep into soil. Instead, it anchors itself with fine rhizomes that grab rough surfaces and absorb water directly through its tissues. After rain, fog, or condensation, the world becomes a vertical reservoir. Water lingers longer in cracks, under ledges, and near shaded corners. The repeated hydration allows the first green filaments to spread. The transformation is slow but profound. A patch no longer than a coin darkens the stone. Then it thickens into a velvet strip along moisture lines. Over months, neighboring spores join in it, expanding outward into miniature cushions and ribbons. The world begins to resemble a cliff face covered in alpine moss. Compressed into urban scale, what makes Mars extraordinary is its ability to create habitat from bare architecture. Its soft surface traps more dust and moisture than exposed stone. The retained humidity supports bacteria, fungal spores, algae, and microscopic invertebrates. Tiny springtails move through the moss like deer in a forest understory. Mice graze on microbial films, spider links ankle soak to the damp green surface. What was once dirt or texture becomes a living vertical substrate. The word's orientation determines the ecosystem. A north-facing word remains cooler and wetter, favoring thick moss carpets and even small ferns in deeper cracks. A south-facing wall may directly supporting early drought-tolerant moss clusters. Near the ground, rising damp creates rich moisture gradients higher up. Condensation from air conditioning units or leaking gutters forms hanging wet zones where moss spreads aggressively. The microclimate creates stacked habitat layers on a single facade. At the base, moss mixes with algae and fungi in dark damp strips. At mid-height, mortar seams host green ribbons and insect movement. Unelected sheltered cushions persist through dry spells. Near windows, condensation creates seasonal moss blooms. The building becomes a vertical landscape. Rain intensifies everything. Water running down our walls follows predictable channels shaped by brick texture, cracks, and architectural edges. Moss grows thickest along the invisible rivers. During storms, droplets gather and live like moss tips, holding moisture long after the rest of the world dries. That turns the mossity into a living sponge facade capable of slowing evaporation and buffering temperature changes. Insects quickly exploit the habitat. Cannot rest in damp cushions. Tiny spiders hunt among the moss tips. Ants expect moisture, cracks for moisture and prey. Some solitary bees may even explore eroded brick holes near moss zones as potential nesting cavities. Birds interact with it too, especially sparrows and small even songbirds. They pull soft moss fragments from walls as netting material, carrying the green fibers to roof gaps, vents, and lattices. In this way, the wall moss ecosystem extends beyond the wall itself into rooftops and neighboring trees. The most fascinating truth is that moss changes the ecological identity of the building. What was once a sealed human structure becomes partially pure and biologically active. Moisture, spores, insects, microbes, and even seeds begin to move along the facade. The wall is no longer architecture alone, it becomes cliff, forest, wetland, insect nursery, blood supply zone, a vertical ecosystem born from patience. This is why old buildings often feel more alive than new ones. It's not just nostalgia or texture, it is the presence of genuine living layers, soft green system quietly rewriting the surface of stone. The word mossity teaches the same lesson as on hidden ecosystems. Life enters wherever time and moisture leave a trace. And on our buildings, the traces become forest. In part 2, we move deeper into the moisture veins inside the wall, where fungi, roots, spores, insects, and trapped water create the hidden internal floor of the vertical forest. The green moss we see on the outside of an oval is only the visible skin of a much deeper ecosystem. Beneath the surface, inside mortar lies porous bricks, cracked plaster, and tiny air pockets. An unseen network of moisture, fungi, microbes, and root-like ferments creates the internal life support system of the world forest. What looks solid from the street is ecologically formed pathways. Ours age like grapes. Grain slowly erodes mortar, head expands bricks by day and contracts them at night. Tiny fractures appear where materials meet. Over decades, the fractures widen into capillary veins, microscopic channels that pull water inward and sideways through the building's surface. This is where the tour mossity begins. After rain, moisture doesn't simply sit on the facade, it enters the hidden veins, moving through minor dust, crumpling mortar, trapped organic particles, and microscopic voids. The world becomes a vertical sponge magic, storing water long after the visible surface looks dry. The moisture vents are the ecosystem's bloodstream. Moisturize creep into the rough edges of moisture seams, drawing repeated hydration from the capillary channels. Algae spread first acting green films inside shaded wet pores. Fungal spores germinate in minor dust pockets. Bacteria colonize every damp grain. The deeper the wood retains moisture, the richer the living layer becomes. In very old buildings, especially brick walls, the mortar itself can become a biological floor. Mortar is porous, rough, and easily traps wind blow particles, pollen, soot, leaf fragments, insect scales, feathers, and fungal spores. Over time, they create microsoil inside the wood joints, enough to support moss expansion and even the first roots of tiny ferns or weeds. That hidden substrate is where fungi thrive. Five-wide mycelial threads move through the damp seams, feeding on trapped organic matter. They bite loose dust into stable clusters, improving moisture retention. In some places, fungi and moss create a cooperative system. Moss traps water on the surface, while fungal networks hold it deeper inside the moisture. The result is a living water battery inside the building skin. Tiny invertebrates turn the veins into active corridors. Springtails feed on mold and fungal hyphae in damp mortar ice. Mice graze on biofilms. Tiny beetles shelter in crumpling plaster voids. Ants may explore deeper fractures where moisture remains stable during hot afternoons. At night, even snails can climb lower wood zones to feed on algae and soft moss edges. The vertical nature of the world creates layered hydrology. Near the ground, rising damp pools crowd water outward through bricks and plaster, keeping the lower facade permanently humid. They often create the thickest moss ponds, dark green carpets hugging the first meter of wall. Mid-level seams depend on rain splash, leaking gutters, and condensation from windows. High up, Roof runoff and mist-driven wind create seasonal wet patches. Under ledges, trapped humidity lingers even during dry weather. Each level forms its own moisture community. That means a single hour can behave like several ecosystems stacked vertically. A wet moss marsh near the base, a fungi same forest in the mortar lies, a dry legend reaches on sunlit bricks, hanging moss curtains under gutters. Temperature buffering makes the internal vents even more resilient. Inside the wall, moisture evaporates slowly. That creates stable cool zones where microbes and fungal mass can survive longer than severe conditions would suggest. During heat waves, the outer moss may collapse temporarily, but the deeper moisture vents preserve life until the next rain. One of the most cinematic parts of their ecosystem is how water moves after a storm. Raindrops strike the wall, some bounce away, some soak into moss cushions, others disappear into invisible moisture lakes. Hours later, while the street is dry, the inner channels still hold water, fungi continue spreading. Springtails keep feeding, mosquitoes slowly rehydrate from below. The world is still alive long after the rain had gone. Human structures unintentionally strengthen their system. Leaky gutters, dripping air conditioners, window condensation, cracked plaster, and weathered paint all create new moisture roots. Every floor in the building becomes another vent for the world forest. That is why the most vibrant most cities often grow on imperfect architecture. The world's hidden vents also connect to neighboring ecosystems. Moisture moving down the facade may drip into sidewalk, cracks below, feeding pavement moss and weeds. Spores released from the wall travel to nearby trees, fences, and rooftops. Insects climbing the most surface move toward balcony gardens and roof ledges. The building becomes part of a larger urban moisture network. What seems like all damage is actually ecological opportunity. Cracked plaster becomes fungal shelter, porous moisture becomes soil, lakes become streams, ledges become wet cliffs, moss becomes forest canopy. The world is no longer just structure, it's a vertical watershed. And hidden inside is a living hydraulic system quietly supporting life on stone. In part 3, we'll step back outside to follow how birds, insects, spores, and rain turn entire facades into migration highways across the neighborhood skyline. By the time moss has spread across mortalized, ledged gutters and damp brick seams, the old building is no longer an isolated ecosystem. It becomes part of something much larger, a skyline migration highway, a vertical route that connects spores, insects, birds, moisture, access across the neighborhood's walls, rooftops, balconies, and trees. From street level, buildings appear separate, but to tiny organisms. Every mosaic wall is a stepping stone and a continual aerial corridor of life. The first travelers are spores. Every time the world tries out terrain, most capsules release microscopic spores into the air. Wind lifts them upward and sideways, carrying them to nearby facades, rooftop edges, drain pipes, outfences, satellite dishes, and even abundant window frames. The city skyline becomes a drifting cloud of invisible biological movement. A single storm can redistribute thousands of spores from one ward to an entire block. Rain has shaped their migration route too. Water flowing from rooftop gutters spills down off facades, carrying fragments of moss, algae, and organic particles. The fragments locked in fresh cracks under lattice and around broken plaster, creating new vertical colonization points. The building is not just a habitat, it's a launch platform. Insects move through the skyline corridor with remarkable precision. Tiny spiders use silk threads anchored to moss tips and ledge corners, allowing them to pollute short distances between nearby walls, glass however, and humid facade zones, especially around window condensation chills. Beetles patrol moss cushions under ledges where prey gathers. Springtails may spread through wet gutters and drain lines connecting several buildings. The most active routes often follow architectural continuity. Water to ledge, ledge to balcony, balcony to drain pipe to neighboring wall, wall to rooftop moss strip. The entire block behaves like a vertical forest canopy. Birds turn their migration highway into something even more dynamic. Sparrows, swifts, starlings, and small urban songbirds constantly interact with moss squirrels. Sparrows pull moss for nesting fires, moving material from facade to roof gaps. Swifts inspect cracks and vents near moss zones for insect prey. Pigeons build perch on warm ledges above damp wall strips, dropping seeds and nutrients that later wash into mortar lice. Each perch becomes a vector of ecological transport. Feathers brush spores loose. Feet carry dust and seeds from tree branches. Bees relocate moss fibers. Droppings enrich ledges and cracks. The skyline corridor expands with aerial flight. At dusk, the system becomes even richer. Most rest on damp wall surfaces where moss creates cooler temperatures. Spiders stretch webs between vines, pipes, and ledges. Geckos are wall leaders, and some climbers patrol illuminated moss zones near windows where insects gather. The facade turns into a nocturnal hunting forest. Seasonality redraws the migration routes. In spring, spores spread aggressively during wet weather. In summer, shaded walls become cool insect refuges. In autumn, leaf dust from nearby trees fills richer moss carpets. In winter, frost opens mortar cracks, preparing new colonization surfaces. The skyline is constantly being rewritten. One of the most beautiful connections happens between our walls and rooftop ecosystems. Moss spreading near upper facades can trap seeds blown from rooftop grasses or nearby trees. These seeds may germinate in gutter debris, creating miniature roof meadows. Rain then washes organic matter back down the wall, strengthening the moss zones below. This creates a two-way vertical ecosystem loop. Moss captures spores, buds move fibers upward, roof plants drop seeds, rain returns nutrients downward. Insects travel the lattice, new wall zones bloom green. The whole building press as one habitat. Human infrastructure unintentionally strengthens the skyline migration route. Air conditioning street lights create permanent wet streaks. Cracked paint traps spores. Rusted metal brackets collect moss and algae. Algae birds act like vines, having spiders and insects bridge gaps between surfaces. Even abandoned buildings become biodiversity towers. Without frequent cleaning or repainting, their walls host thick moss piles, latent fields, fern pockets, insect nurseries, and bird nesting routes. In dense cities, these forgotten structures often become the richest vertical wildlife corridors in the skyline. The ecological importance of the migration highway is enormous. It allows species to move between fragmented habitats where parks and street trees are too far apart. Most squares become mid-air rest stops, feeding points, and moisture refuges. Without the roots, many tiny species would remain isolated. With them, the skyline becomes connected. This is what makes our world feel mysteriously alive. It's not only the green texture, it is the constant unseen movement. Spores drifting after rain, spiders crossing silk bridges, birds harvesting nest fibers. beetles hunting ledges, seeds arriving from roofs, water carrying nutrients downward. The building is not standing still. It is participating in migration, and through that migration, the warm city becomes part of the neighborhood's living circulatory system. In part 4, we close the story by revealing how the vertical moss forests act as cooling shields, moisture banks, and resilient layers for the entire urban block. By the final layer of this story, the award is no longer simply architecture covered in green. It has become a living shield for the urban block, a vertical resilience layer that cools surfaces, stores moisture, shelters wildlife, and quietly softens the harshest effects of city life. What makes the word moss city so important is not only that it supports life, but that it changes the physical behavior of the building itself. Bare walls absorb sunlight quickly. Brick, stone, and plaster heat up through the day, radiating warmth back into alleys, corridors, and streets long after sunset. But when moss spreads across the surface, it creates a soft insulating layer. The green cushions intercept light, trap moisture, and reduce direct exposure of the wet material underneath. This turns the facade into a natural thermal buffer. On hot afternoons, moss-covered sections remain noticeably cooler than exposed stone. Moisture held in the moss slowly evaporates, creating a tiny cooling effect around the wall surface. Across an old neighborhood filled with shaded buildings, it becomes a distributed vertical cooling network, reducing local heat buildup in narrow streets and inner corridors. The cooling effect is strongest in older districts with dense building walls facing each other. Most substance reflected heat reduces glare and creates cooler pockets where insects and birds can rest during the hottest parts of the day. For tiny animals, the cooling layer is a lifeline. Spiders shelter in damp ledge moss. Beetles hide beneath soft cushions near cracked moisture. Gnats hover in cool, humid wall shadows. Springtails remain active longer in moss seams than on dry stone. Geckos or ground lizards patrol the cooler zones at dusk. The world becomes a climate refuge built into architecture. Moisture storage may be even more important than cooling. After rain, the moss city acts like a vertical reservoir. Instead of water instantly evaporating, or running off smooth plaster. The moss captures droplets between leaves and retain as sponge like tissues. The stored moisture slowly fills the internal mortar veins beneath the surface, keeping the ecosystem alive through dry periods. Across many buildings, the moss banks create a distributed humidity system for the block. Corridors stay slightly cooler. Shaded alleys retain moisture longer, where insects find hydration points. Birds locate damp surfaces for nesting fibers. Spores survive heat waves. The building becomes part of the neighborhood's water memory. The resilient layer also supports stormwater control. Moss slows rain moving downwards, reducing splash erosion at the base and feeding moisture gradually into sidewalk cracks, tree pits and drain seams below. In heavy storms, every moss strip acts like a small check dam on the facade, breaking water into slower flows. They create a beautiful ecological loop between wood forest and street forest. Roof runoff face uppermost. Moss slows the water. Droplets drift into pavement cracks. Cracks support weeds and fungi. Moisture reaches tree roots. Trees shade the wall. Shade preserves the moss longer. The entire street becomes linked by vertical and horizontal moisture pathways. Birds and insects benefit at neighborhood scale. Moss-covered buildings produce more prey for squirrels, sparrows, and more songbirds. Nest-building birds harvest moss fibers from a word's egg spring. Pollinators pause on flowering vines that often establish near damp moss belts. Spiders help regulate flying insects around windows and alley lights. The moss city functions as a biodiversity amplifier. It doesn't only support moss, it strengthens every connected ecosystem around it. That becomes increasingly important as cities face climate extremes. Hotter summers, stronger storms, and longer droughts make ridges shield surfaces less forgiving. Moss-covered walls introduce flexibility. They hold water, soften temperature spikes, and provide refuge during ecological stress. In that sense, the moss city is a form of passive urban adaptation. No machines, no technology, no active maintenance. Only time, shade, rain, and living green layers rewriting the surface of buildings. Even the psychological atmosphere of a neighborhood changes. Most walls make spaces feel older, quieter, cooler, and more alive. Humans instinctively respond to the living surfaces. often experiencing shade alleys and mossy dust at calmer than like concrete corridors. The ecosystem improves not only biodiversity but human perception of place. That is why our neighborhoods often feel rich with atmosphere. The walls are not inert. They are breathing with moisture, texture, and life. The most powerful lesson of the word more city is simple. Resilience often begins at soft dirt on hard surfaces. A few spores land, a seam stays damp, a cushion forms, insects arrive, birds harvest fibers, water slows. Haze softens, the whole block becomes more alive. The world, once built to defy and protect, evolves into something gentler. A vertical forest showed quietly helping the city endure. The next time you pass an old building with green seams across its brick posts, the most is not decay, it is isolation, habitat, humidity bank, wildlife corridor, cooling system, a memory of brain held in stone, and in the hidden ecosystems of everyday places. It may be one of the city's most elegant survival systems.